Uh, Good evening. So, in today's problem solving session, we'll discuss some basic problems on compensated design using frequency response approach. So, frequency response approach means we'll be dealing with the Bode plot. So, using that Bode plot, we'll design some compensator that will meet actually the desired specification. So, the specification means both transient as well as the steady state specification. So, in case of this frequency response approach, we will first look for the lower frequency range, which will be directly giving the steady state specifications in terms of the error constant. So the initial slope of the Bode plot in the low frequency range, it will dictate that error constant, and we will first be dealing with this meeting this steady state error specification. So in most of the cases, so first we do with simple gain adjustment, and in most of the cases we will see that by simple gain adjustment we may not meet all the specification, but we can this gain adjustment, because it shifts this Bode plot up and down with this gain value. So this magnitude Bode plot, so we'll have the desired steady state error, but once we adjusted the gain of the system, then the mid frequency range will also change, and we know that this mid frequency range actually gives this transient specification, because in the Bode plot we have this phase margin, gain margin, and the bandwidth all are actually located in the mid frequency range. And we, as you have already seen the lecture video, there is this specification of damping coefficient in the time domain, and this omega the natural frequency can be translated into this quantity of phase margin, or this bandwidth. So this mid frequency range specification will dictate that transient response of the system, and we want a desired response. But once this Bode plot is shipped with this gain adjustment, then we will see that our system specification, that is the phase margin, may decrease, or even the system can become also unstable. So in that case we will need some type of compensator that can give us the desired desired transient response of the system. So what we will do is, first we go for the gain adjustment, then we went for this compensator design. If that specification are not met, then we go for the compensator design, and the compensator means there could be lead compensator or the lag compensator. So in the lead compensator, as we have seen, because it provides some phase positive phase angle within some frequency range, it is called the lead compensator. So this frequency range will be between two corner frequency that are determined by the zero and pole of the system, and because the zero will come first and then the pole, so we see that it's essentially behave as a high pass filter. And using this lead compensator, because it's providing some positive angle, we can actually add some positive angle at the gain crossover frequency to the original uncompensated system, and that's why we can increase our phase margin. But as we see that, because it also provides some gain, so our gain crossover frequency may shift to the right, so we have to somehow take account of that also. Okay, so in the lag compensator, what happens that, because this compensator will provide some phase negative phase angle, it's called a lag compensator, and thus we see that this phase plot is of no use to us, but this magnitude plot, so it will have a low pass filter nature. So if you want to have a phase margin which is located, for example, in a very low frequency range, then we will use lag compensator, and we will take use of the magnitude plot of that, not this phase contribution, because anyway this phase contribution is a lag the negative angle contribution, so it will not give us benefit. But with the help of the magnitude plot, which is essentially a low pass filter, we can shift the crossover frequency, because we can decrease this magnitude original Bode plot magnitude plot, so it will shift this gain crossover frequency to the left, where we may have some higher phase margin. Again, because this lag compensator also gives some kind of negative angle contribution, so we have to take into account in some sense, that is we want this we choose this crossover frequency to slightly left, then the desired point, because of this contribution, that is the lag contribution from this lag compensator. Okay, so in some cases we will see that only this lag or lead compensator may not gives us the desired specification. So what we will do, we will take the combination of that, that is we will use the lag lead compensator to achieve that. And this actually is not an one step method, because we have to take some kind of trade-off we have to do, and we have to repeat our steps so that the desired performance we achieve there. Okay, so now we will discuss some basic problem. So some standard problems we will discuss. So first problem is that, okay, so we are given a phase lag compensator. So what happens when a phase lag compensator is used in a system? Okay, so what happens to the gain crossover frequency, bandwidth, and the natural frequency? Okay, so as I said, or you already have learned this in the lecture video. So in the lag compensator, we make use of the magnitude plot of this lag compensator, which is the low pass filter nature. So it actually, what it did is that it actually adds a decreasing slope of that magnitude plot is added to the original system. So we see that its magnitude will decrease, or in other way, the gain crossover frequency, that is the frequency at which it becomes 0 dB, will shift to the left, right? So the gain crossover frequency will then decrease. Okay, so once this gain crossover frequency is decreased, we also see that the bandwidth also will decrease, because we are shifting, you are adding some negative amount of dB that by this this magnitude to the original magnitude Bode plot. So bandwidth will also decrease, and we see that this bandwidth, this frequency is related to the natural frequency with some damping term. So this exact expression is by this, plus some 4 zeta 4 minus 4 zeta square plus 2. Okay, so this is all in the square root. Okay, I'll just write. So we see that this bandwidth is related to this natural frequency, and this term, so this is multiplied with this. So 1 minus zeta square plus 4 zeta 4 minus 4 zeta square plus 2. Okay, so we see that some function of damping coefficient, damping, and this natural frequency, and this lag compensator, it has very negligible effect on the transient response in the mid frequency range. So the damping coefficient will remain the more or less same. So once this bandwidth is decreased, then the natural frequency will also decrease. So we see that when a lag compensator is added, we shift this gain crossover frequency to the left, and also this has the effect in terms also bandwidth, that will also shift to the left, and so the natural frequency also. That means all things should decrease, that is gain crossover frequency, bandwidth, as well as the natural frequency will decrease for this lag compensator once it is added to the system. Okay, so then we move to the next question. Okay, so in the next questions we have given an open loop transfer function, and it is desired that the compensated system has some specification, that is the velocity error constant should be this is second inverse in the unit, and also phase margin of 40 degree. Okay, so first we have to find the gain crossover frequency of the uncompensated system. Okay, so to find this gain crossover frequency of the uncompensated system, so that means we just equate its magnitude to 1, and we find at what frequency this magnitude become 1. So this is a simple step. So what we will do, let omega jc be the gain crossover frequency. Okay, then we see that the magnitude of this transfer function at this gain crossover frequency should be what? 1, right, by definition, or in that decibel 20 log of this magnitude will be 0. Okay, so the magnitude in simple sense will be 1 at the gain crossover frequency. So that means magnitude of this j omega gc into j omega gc plus 1, magnitude should be equal to 1. So we just substituted this transfer function what are given there, and we equate this magnitude to 1, which implies that we have GC square root of omega GC square plus 1. So we take the magnitude, which is just the square of the imaginary part plus real part square of square root of that. So this should be equal to 1, or implies that omega GC times omega GC square plus 1 should be equal to 1, or we can take the square on the both sides, so it will be omega GC square omega GC square plus 1 equal to 1, or we have omega GC 4 plus omega GC square minus 1 equal to 0. So we have a equation like this. So if we take omega GC square equal to x, so just take it, then we see that it is just simple x square plus x minus 1 equal to 0. So we have a quadratic equation for which we can easily solve, and we find this x, or which is again omega GC square, what we have taken should be the solution of this quadratic equation, and these are, using that calculator we can easily find them, and these values are, because of quadratic we have two values, one is 0.618 and another is minus 1.618. okay, so these are two values, and we see that because this is a real quantity, so this cannot be the value, only this positive term will be positive value will be the root. So omega GC will be then square root of this 6, this is equal to square root of this, it's equal to 0.786. okay, so this is this gain crossover frequency. Okay, so we are asked that this open loop transfer function is given, so we first have to find the gain crossover frequency of the uncompensated system. So what we do is that we just equate this magnitude of this uncompensated system to 1, because this is the definition of the gain crossover frequency, that is where its magnitude should be 1, or in the decibel, that is in 20 log magnitude, in the decibel it will be 0 dB, right? So we just equate it and we solve it. So by solving we get one equation, so that can be transferred into a quadratic equation, and we then find this root of this quadratic equation. So this actually gives this omega GC, or the gain crossover frequency square. Because it is a real quantity, we discard this negative number, we just take this positive number, and which will give us this gain crossover frequency. okay, so this is the gain crossover frequency for this uncompensated system. okay, so in the next question what we do is that we compute this phase margin of the system, this uncompensated system. So we have given this uncompensated system and we compute this phase margin. okay, so to design we first have to, because in the designing process we need to have this specification to be met. So for that we first observe that what is this phase margin is there. okay, then we will see whether we can achieve both this steady state specification as well as the phase margin by simple gain adjustment. If not, then we will look for the compensator. okay, so the phase margin, so to calculate this phase margin we already computed this gain crossover frequency, which is 0.786 radian. So this gain crossover frequency, so the phase margin means what will be the phase angle that actually has the system at this gain crossover frequency, and how much far it from this unstability, that is the minus 180 degree. So this is the definition of the phase margin, or in other words the phase margin will be what, 180 degree minus this angle of the system at the, so this is the transfer function. So the transfer function angle we take at gain crossover frequency, that is the frequency at which its gain is 1. okay, so this gain crossover frequency will put this, so using that we can compute this phase margin. So we see that so this in the frequency it will be omega GC and one term is j omega GC plus 1. So this is the transfer function at this gain crossover frequency. Using that in place of s we just putting that j omega gc. Okay, so this is this. So this, then this angle, phase angle of this will be what? So this is 180 degree minus. So in the numerator there is not term, so this contribution is 0 because there is no 0, and we have two poles. So the first pole, because of this only imaginary part, its contribution is 90 degree, or you can just compute tan inverse of imaginary by real. So the real part is 0, so tan inverse of infinity is minus 90 degree, and minus sign is coming because we are taking in the denominator, that is the pole. Okay, so the minus of tan inverse of, then this imaginary part is this and the real part is this. Okay, or 180 degree minus 90 degree minus tan inverse. So this we already computed omega gc, that is the gain crossover frequency, which is 0.786. Okay. So you just compute this, so it will come out. Okay, just compute it. 180 degree minus 90 minus tan inverse 0.786. So we have 51.83 degree. Okay, 51.8 degree. So this is this phase margin of the original uncompensated system. Okay, so it's actually good, better than what we want, but still we have not made this steady state specification. Okay, so first we made this steady state specification, that is by increase this gain. Then we will see that, so we will not be doing that because it will need this Bode plot. So then we will see that because of this increase in this gain, this Bode plot will be what? It will shift, right? So the magnitude plot is something like that, then it will just shift. So if it just shift, then we see that this gain crossover frequency will also change because we are just increasing this magnitude. So in that sense, this phase margin will decrease for this compensated once we have this gain compensated. Okay, so first we compute what should be the gain, so that we made this specification of this error specification, that is the velocity error specification. Okay, so first we do the gain adjustment. So to compute this gain, so we already know that how to compute this. If the transfer function is given and we are just adding the gain of that to this transfer function, then it will be just some gain times this transfer function. Okay, and in the to compute this steady state, we know that this kV, this is simple limit of SGS when s goes to 0. So this will give this velocity error constant, right? So this transfer function is now this one term after adding some gain to that system. Okay, transfer function. So it's simple limit s time k by s into s plus 1, s goes to 0. So these two s will cancel. So it's just k. And what is this desired kV? So this is, we want 10 second inverse. Okay, so the kV is given 10, then this k should also be 10. So we have to make this gain 10. So in the frequency domain, what we do, first we adjust this gain to meet the steady state specification. So this steady state specification are dictated by the initial portion of the Bode plot, that is the low frequency range, where we have this initial slope. Okay, so we just adding this gain will, what will do, it will just shift above this Bode plot, and this will give this as the desired kV. So for this first order system, what we have a initial slope will be minus 20 dB because of this presence of this pole of the system. So what we did, we add this gain, so it will just shift this point original there, it will shift this initial point, and thus we know that this gain kV is just the frequency at which this initial slope line actually intersect with the 0 dB or the magnitude 1 line. So once it is shifted, then we see that it will, this frequency at which it will intersect will increase. That means our steady state specification kV value will also increase. Okay, but it has the consequence, because of this plot is actually going up. We see that the point at which this gain will become so this is initial slope, but the original plot will be something like that, something like that, or something for that. So this original slope will have what? So for this, okay, because we have two poles, so it will be, okay, we can plot this also. this is minus 20, then it will minus 40 dB, okay, after one corner frequency, this one. So this is minus 20 dB, then minus 40 dB for the Bode plot. So we see that the gain crossover frequency will also shift to the right. Originally it was like this, so it will shift. So that means at that point, because the angle contribution is not changing, because we are just adding some gain, so this angle phase margin will decrease, right? Because the angle plot will not change by simple gain adjustment. So we see that even though the original system has a good phase margin, but once we add this gain, once we adjusted this gain for the system to meet this error constant, because this plot magnitude plot will shift, that is to up, our gain crossover frequency will shift to the right, but because of this adjustment only gain, the phase angle phase plot will not change. So we see that in some sense our phase margin will decrease. Okay, so this can be verified using Bode plot, just using that MATLAB. So you can plot and see it is not meeting that. So I'm just intuitively explaining that. Okay, so we see that our phase requirement may not meet, so for that we will need this compensator. Okay, so now, so we are given this lag compensator. Okay, so what we are dealing with it, okay, I think we have not mentioned about that desired. Okay, but anyway, we can from this we can identify that is a lag compensator because of this value is greater than 1. Okay, so anyway, we have not mentioned that, but now let's assume that this compensator is designed using this parameter. So the compensator is what? So this compensator, so this is without this gain I am writing, so it is okay, the compensator transfer function will be this plus beta times st. Okay, so this is the compensator transfer function, and we are given this beta and t value we are given. So what will be the phase margin of the compensated system? So here we have mentioned this lag compensator. So because of this beta is greater than 1, so this is a lag compensator. So the phase, what will be the phase margin? So for that we have to plot this Bode plot and see what is the gain crossover frequency. Okay, so we are just given that value here, 1 radian per second. So at this gain crossover frequency, what will be this phase margin of this system? Okay, so to see that, we just take this, because this is given as the gain crossover frequency, new gain crossover frequency after adding this compensator. So we take this gain crossover frequency and we just compute this phase angle of this whole system. That is this. What is this whole system? So we have this GC and this original transfer function. These are in cascade. So this product of these two transfer function will be the transfer function of the whole system after we have added a lag compensator. So this is simply equal to 1 plus st plus beta st times 1 by s into s plus 1, and we already have this gain adjusted, this k value we have this, so we can just add this gain k value also, but it will not contribute anything to the phase. Okay, so then this angle will be what at this gain crossover frequency. So okay, this phase margin, so we can directly write also phase margin. So the phase margin is again, so let's denote this by g prime s. Okay, total overall transfer function. Then the phase margin is what? 180 degree minus this phase angle of this transfer function at this gain crossover frequency. Right. So this is the formula for the phase margin. So we see that how much it is from this minus 180 degree angle at this gain crossover frequency, that is when this transfer function magnitude become 1. Okay, so we are given this gain crossover frequency 1 radian per second. So we'll just use this and this form. We are also given beta and also t, so we can just also write this. Okay, so it is 1 plus 10s by 1 plus 70s. Okay, so this compensator form is this, and this other form is original transfer function, this s into s plus 1. So we just compute this angle, so it is just 180 degree, minus from this we have plus tan inverse. For this 0 it will be 10 minus again this imaginary part by real part. So instead of s we will put j omega gc, and j omega gc is 1, so the imaginary part will be this 1 multiplied will be this. Okay, I will just write that so it will be clear. So what we will do, first that for this compensator we put this omega gc, so this will be what, then 1 plus 10, omega gc is 1, so we have 1 plus 10, so j 10 by, in the denominator we have j 70, so this is the value. So from that we obtain that for this 0 it will be tan inverse of imaginary by real, so 10 by 1. Similarly for the pole it will be negative contribution, so minus 10 inverse of imaginary by real, so imaginary is 70, real is 1, so tan inverse 70. And from this k will not contribute, only pole are there, so for only this s turn, that is j omega turn, now it will be 90 degree, and the other turn it will be tan inverse of imaginary by real, so imaginary instead of s we put j omega then to 1, so it is 1 by 1, so it is only 1. So we just compute that. So again we use calculator to compute. So 180 degree, okay, 180 degree, so I just put minus and plus sign will be there. Okay, plus tan inverse of 10 minus tan inverse of 70 minus 90 degree minus tan inverse of 1. Okay, so the angle is 41 degree. Okay, so we see that this is correct answer. And with this compensator design, okay, by choosing this value, we see that we can, even after the gain adjustment, we can achieve the desired phase angle, okay, phase margin. So that was originally desired there, this phase margin was 40 degrees, so we can approximately achieve that phase margin. Okay, so this plus, okay, I just put the negative sign there, the plus, right? So then we move to the next question. Okay, so this, okay, 5 I already discussed this, okay, I will space there. Now 6th question. So now we are given this transfer function. Okay, so we have to find this frequency. Okay, we are given this beta and t for this lag compensator, and we want to find this frequency at which the maximum phase lag occur in the compensator. Okay, so how will go this? So you already know that for lag compensator, okay, we are given this lag compensator, let in the j omega in the frequency case, so it is just j omega t by 1 plus j omega beta t. So this is the lag compensator. Okay, we will have some gain k beta also, so this we can ignore because we want to compute this phase angle only. So this is the lag compensator, and we know that the frequency at which this maximum phase angle will be contributed by this lag compensator is the frequency. So this is the omega m, so it will be just 1 by square root of beta t. Okay, so this you can see from the lecture video. So how to compute this? You just compute this. Okay, so the procedure is very simple. That is the, okay, so space is there. So what we will do, we just compute this phase angle of that. So this phase angle will be what for this? So it will be phase angle of this lag compensator. So this j omega, this it will be tan inverse of omega t minus, this is from this 0, so imaginary by real, and for the pole negative tan inverse of again this imaginary, which is omega beta t by 1. So real part is 1, so we can just write it omega beta t. Okay, so real part is 1, so this and you can use this tan formula. So this is what tan formula, tan inverse of A minus tan inverse of, let's write it properly. So tan inverse of A minus tan inverse of B is simply equal to tan inverse of A minus B by 1 plus AB. Okay, so using that we can write it tan inverse of omega t minus omega bt by 1 minus omega t times omega bt. Okay, then you take this, because this is the phase angle, so you take this derivative with respect to omega. So it is already done in the lecture video. So then from which we can compute this frequency at which this derivative will be 0. Then we compute that and we find this omega term frequency at which this maximum phase angle will occur. Okay, so this is the formula for this maximum phase lag. So at this frequency, this maximum phase lag that is given by this lag compensator will occur. Okay, so once we have this do term for this lag compensator, we can easily compute that just substituting that. Okay, so this is just 1 by square root of beta 7 into 10. Okay, so it's 0.0378. Okay, so the first term. So this is the frequency. So as you can see, this frequency is very small also, because we add this lag compensator to change only in the lower frequency range. Okay, so as you can see, at this point this lag compensator will give this maximum phase lag, it will contribute to the system. Okay, so then we move to the next question. So we are again given a lead compensator. So this is okay, so we are just not given the gain, so this is just in the S domain is st by 1 by alpha time st. Okay, so this is this, and alpha should be less than 1 for this lead compensator. So this is this form it is given. So what is this maximum phase shift that can be obtained from this lag compensator? Okay, so we already have this formula, so this formula also work for this also. Okay, because you can see this form are exactly same, right? Only this alpha is less than 1 here. Here this beta will be greater than 1. Okay, so this formula will work, that is the frequency at which this maximum angle contribution will be. Now what, this instead of beta we'll put this alpha. Okay, so square root of alpha t. So this is the frequency at which this maximum phase shift by this lead. So this will be a positive angle contribution because of this lead compensator, this will occur. And so once we have this, we can easily substitute it in the angle formula and find what will be this angle of this compensator at this frequency, because this is the frequency at which this maximum phase angle will occur. Okay, so first we compute this t and alpha by comparing these two transfer function. Okay, so t is simple, it is 0.12. Okay, so alpha value will be what then? So because this term is alpha time t, right? So alpha time t, it is given 0.04, and t we have this, so alpha is simple, we just divide them, it is the 0.04 by 0.12, so it is 1 by 3. Okay, alpha is 1 by 3, and it is less than 1 also, as you can verify. So we have this, then we see that okay, we will take this form, so and see what will be this phase angle at this frequency point. Okay, so we'll just use this general form first and see what this term is coming. Okay, so this is the compensator, this 1 plus j omega t by 1 plus j alpha time omega t. Okay, so this is the lag compensator using this frequency. Okay, imaginary frequency j omega, so that is directly coming from this by putting s equal to j omega. So this angle contribution then what? So this is tan inverse of omega t minus tan inverse of alpha omega t. So again this imaginary by real part. For this 0 this is positive, for this pole this is negative contribution, and this frequency at which this maximum phase shift occur is this frequency, right? So we will compute this j omega m, okay, at this frequency, this angle contribution, and this omega m is what? It is just 1 by square root of alpha t, okay. Substitute that. So tan inverse of, okay, omega t, it's just omega, instead of omega we will use omega m, and omega m value this, so we will use 1 by square root of alpha times t minus tan inverse alpha times 1 by square root of alpha t, okay. So it is just tan inverse 1 by square root of alpha minus tan inverse square root of alpha, right? So this square root of alpha and this will give square root of alpha, and t will cancel. So this again we can use this tan formula, that is tan inverse of a minus tan inverse of b equal to tan inverse of a minus b by 1 plus ab, okay. So this will give what then? Tan inverse of 1 by square root of alpha minus square root of alpha, so this is a and this part is b, right, by 1 plus a into b, so 1 by square root of alpha into square root of alpha, it is 1, so it is equal to tan inverse of, you can take this first in the denominator, it will be 1 by square root of alpha minus square root of alpha, what will happen? This, so we have, okay, I will use red color, so it is 1 by square root of alpha minus square root of alpha, so you can write this 1 square root of alpha, square root of alpha will be alpha by this, right? So I will use this, so it will be 1 minus alpha, and this square root of alpha times this is 2, right? So 2 into square root of alpha. So this is this angle contribution at this maximum, this frequency at which this maximum angle phase shift will occur. So this is this angle will come, or in the sine also, from tan inverse you can convert into sine inverse, so it will be 1 minus alpha by 1 plus alpha, okay. So this also derived in the lecture video, I just derived it for convenience. So you can use either of this formula and find. So once this alpha is given, you can find this using directly also for this formula without going through all this step, okay. So this is angle, so we'll just compute this. So tan inverse of, so alpha is what? Here we have computed this 1 by 3, so we'll put this 1 by 3 here. So 1 minus 1 by 3, it is 2 by 3, so tan inverse 2 by 3, and in the denominator 2 times square root of 1 by 3, right? So just simplifying that, it will come 30 degree, okay. So it will be tan inverse of 1 by square root 3, so 30 degree. Or also from the second formula, this one sine, it will be what? The sine inverse of 1 minus alpha, it is 1 minus 3, so it is 2 by 3, and 1 plus alpha, 1 plus 1 by 3, alpha is, okay, alpha is 1 by 3, okay. So 1 plus 1 by 3, it is 4 by 3, so it is equal to sine inverse of half, so which is again 30 degree, okay. So this is the answer. So at the frequency at which it contributes to the maximum phase shift, the angle will be 30 degree, okay. So you can directly use also this formula, this last one, this one, to compute this without also going through this written step, okay. So this is how you compute this angle, that is the maximum contribution from this lead compensator, okay. So the next question will be, okay, so we are again given an open loop transfer function, and we will again go through the steps in each of the question. So first we want to have the desired error constant kb, okay. So for this, so what we will do, we will just simple gain adjustment, because it is shown that by adjusting k you want to find this desired error constant. So again we just use this formula. So what is this formula for this kV? This limit of s times gs when s is goes to 0. So it will imply that s times k by s into 1 plus 2s, s goes to 0. So it's simple, s will cancel and this is 1 because s is 0, so it is just k, and desired is 10, so k will be 10. So by simply adjusting this gain value to 10 we can achieve this error constant. Okay, so the next question what we will do, so we are given that we want to achieve this error constant. So what will be the gain crossover frequency of this gain compensated system? Okay, so the gain compensated system means we wanted this error constant to be 10. So that means in the first question we see that by taking k equal to 10 we can achieve this desired error constant. Okay, so this gain compensated system will now then become what? 10 by, because k equal to 10 s into 1 plus 2s, and we want to find the gain crossover frequency for this gain compensated system. Okay, that achieves this error constant. Okay, so this is the gain compensated system, and for this gain compensated system, so how to find this gain crossover frequency? Again using the definition, at this, if omega gc is the gain crossover frequency, then at this frequency the gain will be, the gain for the system should be 1, right? So first we write in the frequency domain this transfer function. So this transfer function is what? In the frequency domain, so we can write here g j omega, so it is just k by j omega times 1 plus 2 j omega. Okay, just substituting j omega instead of s. Okay, so the magnitude of this will be what then? J omega, it will be k by j omega to 1 plus 2 j omega, this magnitude. Okay, so we want to find the frequency at which this gain is equal to 1, and we have denoted it by omega gc. That means that omega gc value, the gain crossover frequency, this magnitude should be equal to 1. Or we just simplify then this expression. So this k, okay, k we already have this k value, so we can just substitute k value. We already have 10, therefore okay, k equal to 10. So we have then magnitude 10 by omega gc square root of 1 plus this would be 4 omega gc square. Okay, so the magnitude is just real square plus imaginary square. Real part is this 1 square, plus this imaginary part is 2 omega gc j, so it will square will be 4, imaginary part is 2 omega gc, so square of this will be 4 omega gc square. Okay, of square root of that equal to 1. So this magnitude, and we just simplify that, so it will be omega gc times 1 plus 4 omega gc square root this equal to 10. So we just take square on the both sides, so it will be omega gc square for omega gc square plus 1 equal to 100, or we just take all the term into one side, so it will be omega 4 omega gc 4 plus omega gc square minus 100 will be equal to 0. Again we see that we can take omega gc square equal to x, so this expression will be what then? 4x square plus x minus 100 equal to 0. Again we have a quadratic equation in x, we can solve that quadratic equation using calculator. So x will come, or x, we have taken x equal to omega gc square, so omega gc square will be from this quadratic expression, we just find the root. So this root are, one is 4.877, so I am just using calculator to calculate this, and another is negative minus 5.127. so we discard this negative one because this is square of this some real part. So we take this positive term, and from that we get omega gc equal to square root of 4.877, and this is equal to, it's coming 2.208 okay, radian per second. So this is this gain crossover frequency for this gain compensated system. Okay, so next we move to then, okay, we have this open loop transfer function, we already have this gain compensated system that actually meets this kV. So this k we have taken 10, and we see that actually meets this error constant. In the previous question we have seen that. So now we find this, what is the phase margin of the gain compensated system. Okay, also in the previous question we computed this gain crossover frequency. So this gain crossover frequency is what? So we have 2.208 radian per second. Okay, so this is the gain crossover frequency. So this phase margin will be what? Then how much angle it is, away from this minus 180 degree at this gain crossover frequency when the system gain is 1. Okay, so again we will use this. So this is gain crossover frequency angle. So this, okay, sorry, I'll just directly write this formula for the phase margin. So phase margin formula will be what? So the phase margin will be what? 180 degree plus this angle contribution by this at the gain crossover frequency. Okay, so it is 180 degree, and from this transfer function this k will not contribute to the angle. So we see that this s will be what? Okay, I will just write here g j omega gc. So it will be what? K is 10 by j omega gc times 1 plus 2 j omega gc. Okay. So it's equal to 10 by j omega gc times 1 plus 2 j omega gc. Okay. So the angle then for this, it is imaginary by real, so it is tan inverse of infinity, so it's 90 degree, minus of, for this it is tan inverse of 2 times of omega gc by real part is 1, so 2 omega gc. So it is 180 degree minus 90 degree minus tan inverse 2 times 2.208. So omega gc we have already computed this gain crossover frequency as this. So from that we just compute this using calculator. So it's coming to be 12.8. Okay. So this is this phase margin. So we see that it's very poor for this gain compensated system. Okay. So the next question we see that, okay, we will be using a lead compensator to improve this phase margin. So just take this lead compensator alpha to be this. So the lead compensator is what? This lead compensator. So in the S domain it is k times alpha 1 plus st by 1 plus alpha st. So this is this lead compensator. So this will be the magnitude. You can also denote it by k prime, k times alpha. So it will be k prime 1 plus st by 1 plus alpha st. Okay, so this alpha value is given. Okay, so this alpha value is given 0.2. So we see that alpha is less than 1, so it is a lead compensator. So what should be the gain crossover frequency such that the phase contribution from this lead compensator is maximum for the uncompensated system. Okay, now we are considering the system without any gain. Okay, so for this system, okay, so what will be the the gain crossover frequency such that the compensator, this compensator with alpha equal to 0.2 will contribute this maximum phase, okay, positive angle at this gain crossover frequency. Okay, so how will then proceed? So first we see that we have this desired kV value to be 10. Okay, so we already computed that this gain should, in this previous case when we just had simple gain adjustment, we see that we can take k equal to 10, then we can achieve this desired steady state error. Okay, so we can take this here. Okay, so this gain, now it's come with compensator, so this gain we can take 10. Okay, so now what this compensator become then? So 10 times 1 plus st by 1 plus 0.2, because alpha is given 0.2 st. Okay, so this is this compensator. Just keep it in alpha also. We will put later that alpha. Okay, so this is the compensator that can achieve this desired angle. Okay, desired error, velocity error. So the question is, what we are asked is that, so we want the gain crossover frequency be such that the angle contribution from this compensator will be maximum at that. Okay, so how will then proceed? We will already know that for this compensator the frequency at which this angle contribution will be maximum. Okay, so that thing we already discussed here, right? So this formula, this is the formula that actually gives this 1 by square root of alpha t. So this is actually gives the frequency at which the maximum phase shift actually given by that compensator. Okay, so we'll first write that. Okay, so we'll write, so okay, here we have this compensator. For this lead compensator, the frequency at which the maximum phase shift will occur is what? This one, right? Square root of alpha t. Okay, so we want that maximum phase shift to occur at the gain crossover frequency. So then what this mean? We should choose this frequency to be the gain crossover frequency, right? Why? Because we want that the phase contribution from the lead compensator to be maximum at this gain crossover frequency, but we see that this frequency is this one. For the lead compensator, this omega m is the frequency at which it will contribute the maximum phase lead, right? So this, if we want this maximum phase lead to occur at the gain crossover frequency, then we should take this frequency at which this compensator is giving the maximum phase lead. That frequency we should take as a gain crossover frequency. Okay, is that clear? Because this is this has to be clear to solve this problem. Okay, so we want the contribution from this phase, this like lead compensator to be maximum at this gain crossover frequency. So we want to compute this gain crossover frequency. Okay, so and we see that the compensator can provide maximum phase lead at this frequency, right? So if we want this contribution phase maximum contribution at the gain crossover frequency, then we must choose that gain crossover frequency equal to this frequency at which this compensator is providing the maximum phase lead. Okay, so but we see that we cannot choose it directly because we are given alpha but we are not given t. Okay, so we have to find also t to find this gain crossover frequency. Okay, so we will see that we will not need t. So how? So first we will see at this frequency, okay, omega m, at which this lead compensator is providing the maximum phase angle, what is the gain of this compensator? Okay, so we'll just first compute that term. Okay, so we are given this compensator, so I'm just writing the frequency domain. So it is k times 1 plus j omega s by 1 plus j alpha time, okay, sorry, omega s to t, right? T, so alpha time omega t. So this is this lead compensator. Okay, so and we want to find this magnitude of this lead compensator at this frequency omega m. Okay, the frequency at which it is providing the maximum phase lead. Okay, we'll see what its gain is and we will find that it is independent of t. Okay, so then what is this magnitude? So we see that this is k times magnitude of this, we'll just square root of this 1 plus omega square t square, so omega m square t square by square root of 1 plus alpha square omega m square t square. Okay, and omega m we already computed this one, alpha by t square root of. Okay, so see that it is k times 1 plus omega square, then it will be what? So omega m square will be 1 by alpha t square, right? So we substitute that, so it will be 1 by alpha t square times t square by 1 plus alpha square times 1 by alpha t square times t square square root. So this is equal to k times, this will be 1 plus 1 by alpha square root by square root of 1 plus, so this alpha will cancel, t square will cancel, so 1 by alpha. Okay, so you can take it to be okay, so yeah, yeah, I can take it. Okay, k alpha plus 1 square root by this alpha. Okay, I'll just write all the steps. Okay, that's clear. So it is equal to then k times alpha plus 1 by alpha square root of this by 1 plus alpha square root. Okay, so it's equal to k times 1 plus alpha square root by 1 plus alpha square root, and we have 1 by square root of alpha. Okay, this alpha. So these two term will cancel, this term and this term. Okay, so then what we will find? It is just simply k times, okay, I'll write here, k by square root of alpha. So this is the gain, and we see that it is independent of t at this maximum frequency at which this maximum phase would occur. This gain is this one, k by square root of alpha. Okay, so then what we want? We want this frequency to be the gain crossover frequency by our earlier argument. So then what will happen? This overall gain of this system at this frequency, it should be 1, right? So we'll write this transfer function. So this transfer function will be, overall transfer function will be what? This compensator in cascade with this original system, right? So the overall transfer function is this, and we want that magnitude at this maximum phase shift that is given by this compensator to be 1. Okay, because that is what we have already observed, that we want that to be the gain crossover frequency. So at this omega m we want this gain to be 1. Okay, and we have computed this gain. Here we have computed is k by square root of alpha for this compensator. So we have this square root of alpha, and now we'll just compute this gain of this system at this frequency. Okay, so we have given transfer function this. So I will write this transfer function. So it is so j omega will be what then? From this 1 by j omega times 1 plus 2 into j omega, right? So it is 1 plus 2 j omega. So this is this transfer function, and okay, sorry, okay, just give me a minute. Yeah. So this is this transfer function, right? So this transfer function, so okay, so this transfer function, so then we compute this magnitude of that. So what is this magnitude of this then? This one. So it is simply 1 by, so in place of omega we are taking omega m. So it is omega m square root of this one. So it is 1 plus 4 omega m square. So this is this magnitude of this transfer function, this one. So we have magnitude of this into this should be equal to 1. Okay, so we then solve, and you can see that we know alpha, we don't know omega, this one. We want to solve this one, right? So we just solve this. So we put the alpha value. Okay, alpha value is what? It is given 0.2. Okay, so we'll put that one. And k value, we already have this compensated system for this kV. So k value we already computed it to be 10, right? Here we have mentioned that. Okay, in the beginning question, here, this one, right? We computed this k should be 10 to have this desired kV value. Okay, so in this question we are given that the desired kV is 10, so k equal to 10. So we can substitute all this quantity. So we are given k 10. We have computed that to have this desired steady state error, and alpha is given 0.2, and this is other are unknown term. Okay, plus 4 omega m square equal to 1. So what we will do, just simplify them and solve this. So again we will get a quadratic equation. So in other words, this is omega m square times 1 plus 4 omega m square root of this equal to, so I will take this into other side, then it will be 10 by square root of 0.2. I will take square on the both side, so it will be, sorry, this will be only this side. magnitude square, because it will be magnitude will be what, omega m square root, right? So it is this omega m. Okay, so this one. So okay, so as you can see, this magnitude will be omega m square root, so it will be just omega m, not omega m square, because the real part is 0 square plus omega m square, imaginary part, and square root of that, so it is just omega m. So I just made some mistake there putting square. Okay, it will be omega m. So I have take square of this, so it will be omega m square times this will be square root term will remove, so it will be this omega m square, and it will be 100 by square root of this square will be this 0.2, and it is 500. Again we will just solve this, so it will be 4 omega m 4 plus omega m square minus this will I take other side, so it will be 500 equal to 0. Again we will take omega m square equal to x, so this equation will be 4x square plus x minus 500 equal to 0. Again we have a quadratic equation, we can just solve for x, and using that calculator, so this x value will come okay, so x or omega m square, it is 11.056, and another is minus of 11.306. So again we will just discard this negative number, we will take this positive, and the square root of that will give this omega, so omega m will be square root of 11.056, and will come 3.325. okay, and as earlier I said, we want this frequency at which this compensator is giving this maximum phase contribution to be the gain crossover frequency. So we will take omega gc equal to omega m, so we can write this is also equal to omega gc, that is the gain crossover frequency, and we find that this is the answer. Okay, so what we did is that we want, so I'll just again say all the steps. So we wanted this phase contribution to be the highest or the maximum that can the compensator can give to occur at the gain crossover frequency. Okay, so we see that, but we already know that this frequency at which the compensator can give the maximum phase contribution is this omega m given by this formula. So if we want this maximum phase contribution to be at the gain crossover frequency, then we must choose this as the gain crossover frequency. Okay, so we solve for this, but we are not given t. Okay, we are just given alpha, but we see that we can, because we are taking this as the gain crossover frequency, at this frequency the overall transfer function magnitude should be equal to 1. Okay, so we just computed the magnitude of the compensator, we computed the magnitude of the uncompensated system at this frequency, and we want that magnitude to be 1. Okay, and we are given that we want the desired kV to be 10, so we already computed what should be the gain to achieve this kV, and that k value was computed to be 10. So we just substitute that k value here, alpha is given, then we can easily compute this omega m at which this overall transfer function magnitude is 1. Okay, we just calculated this, so these are just simple calculation, all steps. So and we find this omega m to be this, so this is the frequency at which the compensator, lead compensator will give the maximum phase angle contribution. Okay, and we want this frequency to be exactly same as the gain crossover frequency, so we take this omega m to be the omega gc, and that actually give this solution. Okay, this one. Okay, so then we move to the next question. So okay, so we already have this choice for this system omega m alpha, so then we want to find this location of the pole. Okay, so once we had both terms, then we know that we can compute this location of the pole easily, right? So how we will go? So we know that omega m, the frequency at which this maximum phase shift occur, given by this formula. Okay, so we'll write this formula again here, 1 by square root of alpha t. So and we computed omega m to be this frequency. Okay, so this is implied that this will be omega m, so 3.325. we know alpha, so we can compute t, right? Alpha is given 0.2 in t, so imply that t equal to 3 point, okay, so 1 by 3.325 times 0.2, so this comes to, so this value is 3.325 times square root of 1.2, so it's 0.6725, okay, around this t value. So then what will be this lead compensator? Okay, so this is the lead compensator, right? This one, as you can see, this is the lead compensator. We take this gain to be 10 there, already we have designed that, we know T and we know alpha, so we can explicitly write this compensator, the lead compensator. So this, what is this lead compensator? It is gain times 1 plus st by 1 plus alpha st, okay. So we'll just explicitly write, so k we already have 10, this is 1 plus t value, which is this, so it is 0.6725 s, this is t value, and alpha time t, it's into 0.2, we'll just multiply that, so it is 1 plus 0.1345 s, okay. So this is alpha time t and this is t, we just substitute that. So this is this compensator, okay. This is the overall lead compensator. And to find the location of the pole, okay, so how to find the location of pole of a transfer function? We just make the denominator equal to 0, okay. So denominator should, the value of the s, that will make the denominator equal to 0, or the root of the equation in the denominator will give the poles of the system, right? So what we do, we make this denominator equal to 0, that is the 1 plus 0.1345 s equal to 0, so it will give this pole of the system. So s will be then equal to what? So minus 1 by 0.1345, okay. Just compute that, so that's 1 by this value, so it's actually minus 7.4349, okay, or approximately equal to minus 7.435. so this is the closed loop form, okay. So this step is just direct. So once we had all the design parameter, we can just simply explicitly write this compensator, and then because we already have this t and alpha value, we can just explicitly write the compensator, and from that can directly figure out this pole of this compensator, okay. Okay, so these are the questions. So any doubt you can ask, okay, so regarding any question or any concept. Okay, so if no doubt, then okay, we can okay, close this session, okay. Or if you have doubt, you can also ask, or you can post in the discussion forum also, okay. So we'll stop this session now, okay.